All right, guys, how's it going? So today I wanted to go through and just work some of these PV equals NRT problems to give us a little bit of a look into how these calculations can be done. So I have several problems here, and we're just going to work our way through them. All right, let's get to it. Now, one thing I like to do whenever I realize that this is a PV equals NRT problem is just to, of course, write it down. PV equals NRT. So how do I even know that this is a PV equals NRT problem? Well, for starters, we're talking about a gas, hydrogen gas, H2. We have volume that is given to us. We have a temperature and we have a pressure. Now, we have all of that, and it's asking us to calculate the number of moles. So we have volume, temperature, pressure, moles. That's everything but the ideal gas constant, which we know. So with that, we know it's going to be PV equals NRT problem. So we are looking for moles. That is our goal. That is what we're after. So if we go through and we change this up algebraically, we take the RT and move them to underneath this side. We will have PV over RT, and that's going to equal moles. Now, once we have this, we can just automatically plug and chug. But we want to do check a couple of things first. What are these numbers that they've given us? They've given us liters. They've given us atmospheres. And I'm going to put a little thing here for the gas constant. And they've given us Celsius. Now, we don't want Celsius. We always want Kelvin. It's easy enough thing to convert over. So if it's 0 Celsius, it's going to be 273 Kelvin. So I'm going to just switch that over to Kelvin. Now, what is the ideal gas constant that we're going to be looking for? It needs moles, liters, atmospheres, and Kelvin. So it's going to be liter atmospheres per mole Kelvin. Now, if you look, the liters are going to cancel, the atmospheres are going to cancel, and the Kelvin are going to cancel. And now we're left with 1 over mole. So a reciprocal of a reciprocal is just normal. So it means moles equals moles. We know we have this set up now. Dimensional analysis can save us every time. So now we know everything that we need. We have the liters here, atmospheres here, Kelvin we converted from the 0 Celsius here, and we also know which ideal gas constant we need. If we look back at the chart, it's going to be this guy here, 0.08206. At this point, we can just start plugging and chugging. 8.56 liters times 1.5 atmospheres over 0.08206 liter atmospheres per mole Kelvin, and then multiply that by 273 Kelvin. All right, and this should lead us to moles. Okay, so let's go through and actually calculate this out. 8.56 times 1.5. And then we're going to divide by 0.08206 times 273. And that's going to get us 0.573. So there we go, 0.573 moles. So that's going to be our answer there. Pretty simple. At this point, it's just kind of basic algebra that you're running through. Next one. So a sample of ammonia gas has a volume at a pressure. So already we're hearing volume and we're hearing pressure. At that point, PV equals nRT should be on your mind. The gas is compressed to a volume of this at a constant temperature. What is the pressure? What is the new pressure? So the sample hasn't changed, so the moles are going to stay the same. Here we're going to have PV or P1 V1 equals N1 R1 T1. So this is going to be our first state that we're in because something is changing. Then we're going to have P2 V2 equals N2 R2 T2. Now here's the thing. Did the moles change? No, the moles didn't change. So N's are going to be the same. Ideal gas constant, it's a constant, it's going to stay the same. And it says here we are at constant temperature, so the temperature is the same. So if all of this is the same as this, we can rewrite it as P1 V1 equals P2 V2. So again, that's just algebra. So if that's the case, well, what do we know? Do we know pressure at the start? Yeah, we know pressure at the start. There's our P1. Do we know volume at the start? Right here. So this is going to be our volume at the start. Do we know the pressure at the end? Well, that is what we're asking for. So this is going to be what we are going to be looking for. And last thing we need to know is volume at the end. Here's our V2. There's our volume at the end. So we just need to rearrange this to where P2 is on one side alone. Divide both sides by V2, and we have it. Now it's just a matter of plugging and chugging. Let me... So it's a matter of plugging and chugging. P1 is 1.68 times volume 1, which is 7. And then that divided by the 2.7, the new volume. And that's going to lead us to a pressure of 4.35, repeating atmospheres. Now, does that make sense? You can always go back and do a little bit of a sanity check to make sure that you're right. Now, if I took 7 mils of something and I compressed it down to 2.7 mils, what's going to happen to the pressure? The pressure is going to go up. So does that make sense? Yeah, that makes a fair amount of sense because our new pressure is quite a bit higher than the original pressure. So we're done with that. All right, next one. So a sample of methane gas has a volume of 3.8 liters at 5 Celsius and is heated to 87 Celsius at a constant pressure. What is the new volume? So we're going to use the same idea here. We have two states. So P1 V1 equals N1 R1 T1, P2 V2 equals N2 R2 T2. Now, what's the same and what's different? Pressure. Did the pressure change? Nope. It says constant pressure. So these guys are the same. The number of moles. It doesn't say we added anything. There's no chemical reaction, so number of moles stays the same. This stays the same as well. So the only thing that really matters is the volume and the temperature. So what we're going to do is rearrange these guys to where they equal each other. And to do that, we do V1 over T1 equals nRP, and then V2 over T2 equals nRP. And remember, the moles didn't change. R constant is always the same, and pressure didn't change. So these numbers in these two different states are going to be the same. So we can now say V1 over T1 equals V2 over T2. And we have everything. We're looking for the new volume. So this is the guy that we're looking for. We can rearrange, and we have everything else. We can rearrange these guys to where times T2, that cancels, and we're done. Okay. Multiply both sides by T2, and we're done. So we are going to have to do one more thing, and that is change this to Kelvin. Some of you more math-minded people might look at this and say, do I really need to change it? Not in this case, but best case or best practice would be just do it anyway. So let's go through and change these guys to Kelvin real quick. All right. So changing these guys to Kelvin, 5 plus 273 is 278. And the other one is going to be 359. Okay. So let's go through and do this. All right. So we're going to be doing V1, 3.8, times T2. So we're looking at T2 now, which is this one, 359, divided by T1, 5 degrees, so this. So 278. So now the new volume is 4.9. Now, does that make sense? Let's think about it for a second. If I increase the temperature of something, of a gas, what's going to happen? If I increase the temperature of a balloon, a gas within a balloon, what's going to happen? Remember the video I showed you guys in class about putting a balloon in liquid nitrogen? It shrank down, and then when it warmed up, it expanded again. Same concept here. If you increase the temperature of a gas, it's going to increase its volume. So that works. Okay. All right, so those were just 3 examples of this. You can basically use that those processes to go forward and solve just about any PV equals nRT problem. If you need more help, let me know. Essentially, it really does come down to just algebra. Remember a few things whenever you're doing calculations in chemistry is always check your units. If your units are good, if your units make sense using dimensional analysis, it should be fine as long as your units are making sense. So make sure to check that. The other thing that you might want to think about doing is separating out your states. Make sure that you have kind of a before scenario and then an after scenario. So making sure and label P1, P2, things like that. One thing you might want to try is actually making a little chart. So P, V, N, T, and then having state 1, state 2. If you do that, you should be able to go through and say, okay, volume is 3.8 here. And oh, what's the new volume? So I know this is going to be my X. This is going to be the thing I'm looking for. Now, pressure. Okay, what do they say about pressure? Constant pressure. Okay, so the pressure didn't change at all. So whatever it is, it's going to be the same. I don't need to know it. All right, N. They don't talk about a reaction. They don't talk about adding gas. So this is going to be the same. So it doesn't matter what it is. It's the same. And state 5, 5 Celsius, and 86 Celsius. Okay, so I know everything about these systems now. And I can figure out, and I already have identified what it is that I'm going towards. So this is going to be, this might be helpful to make a little chart like this to help you organize the information that they gave you in the little story. Feel free to do this. It doesn't take you that long to do, and it can really help you identify what it is that you are looking for. All right, that's all I'm going to talk about today. You guys have a good one, and I'll see you later.